Okay, so now we're going to be graphing rationals, but this time we now have calculus behind us, so we can find relative extrema and concavity to get a much more precise graph with these. So it still starts the same way. You need to find the domain, the holes, the vertical asymptotes, and then the horizontal or slant asymptotes. So the first thing you want to do is factor. So this would be x minus 1 and x minus 1 all over x plus 1. And so you can verify in the graph that nothing's canceling by looking at the calculator. We have a vertical asymptote. So if that x plus 1 was to cancel, there would be no vertical asymptote. It would be a hole. But there isn't. No canceling, no hole. So we know that's good. Now our domain, our denominator cannot be 1, negative 1. And then we just transfer that to our vertical asymptote as x equals negative 1. And now we can go to negative 1 right over here and draw a vertical asymptote. Now, if our top degree is bigger than the bottom, we already know this is going to go off to infinity. So we are going to get a slant asymptote. So we do our long division. And you can then now convert that to synthetic. So we end up with 1, negative 2, and 1. Negative 1. So we bring down 1. And there's our remainder. And so now that we've done limits a lot more, you now know that this is x minus 3 plus 4 over x, plus 1. That's our y equals. And remember the limit as x approaches infinity, this goes to 0. So we end up with just plain old y equals x minus 3. So now we want to graph that. So we go to 1, 2, 3, up 1 over 1, right there, and right there. And we draw our dotted line like that. Now I'm going to take and rewrite this to where it looks a little bit nicer. This way we have some room to graph our different regions. And plugging it in the calculator, we already know that's what it looks like. I have now inputted the x minus 3 in there, and you can see it checks perfectly. Then if you look at our graph, we're going to be getting a local min here and a local max here. So we're going to need our first derivative. And I've already done that for us. So here is our first derivative. And so we do it the same way. We factor the top. So this would be x plus 3, x minus 1 over x plus 1 squared. And then the top would give us x equals 3 and x equals 1, right? So we set the top equal to 0, bottom equal to 0, but that is a domain issue. It's a domain no-no. So all we have to deal with is our 1 and 3 and the domain. So we still have to put that on there because it's a vertical asymptote. So we're going to I like to just draw a vertical line here at negative 1 and even put like a little open dot here. And then looking at our graph, I already know I made a mistake because that's supposed to be negative. So you can see there's something on the other side here of our vertical asymptote. We're getting 1 to the left and 1 to the right. So 1 to the left and 1 to the right. So let's move this over, put it in the middle, and then put negative 3 over here, positive 1 over here, and we do our derivative tests. So f prime of negative 100, f prime of negative 2, f prime of 0, it's a good one, and then f prime of 100. And then we just need to test these numbers. Now the bottom's squared. Don't have to worry about it. It's just the top. So if I plug in negative 100 in here and a negative 100 in here, I'm going to get negative and a negative, which means that is a positive. We are increasing. And then at negative 2, that would become positive and negative, meaning we are getting a negative and it's decreasing. And then 0, that would be positive and negative. So we are also getting a negative, so it's decreasing. And then the last one would be positive and positive because it's, well, 100. And so we know it's positive increasing. And then again, we verify with our calculator to make sure it's right. So we are increasing and then decreasing and then decreasing and then increasing. Everything's checking out. So now we just need to find those points. So trace negative 3 should be perfect. Yep, and it's negative 8. Let's write that. And then we also need to test 1. And that's at 0. So that is our critical points now. And then always test that undefined value as well, just to make sure and see it's not even there. Okay. So we have a local max here at 3, -3, -8. What the heck happened there? -8. And then we have a local min at 1, 0. And then it's increasing from -infinity to -3. Oops, I need to put a little more room in there, so I'm going to zoom in. -infinity to -3, union 1 to infinity. And it's decreasing from -3 to -1. And you cannot say this. If you put -3 and then you put comma, -1, comma 1, it's wrong. There's a split there. So -1 is not included. It's an undefined value. So you still have to split them up just like that. So there you go. That's why you have to put your domain issues on there. Okay. So now we know that we have a maximum here at -3, -8. And we have a local min right here at 1, 0. Put it below because I know it's a min, like that. All right, so now we just need to test our concavity. We already know it's going to increase and decrease, so we could already verify it. But let's just make sure that the concavity is correct. So if we plug this in, right, we get nothing for top, right? So on the top, we get none, no points of inflection. And on the bottom, we have our domain issue again. It's a domain no-no. So the only thing we have to put on here is our undefined value, our open dot. So we're going to test to the left. So f double prime of -100. And we're going to test f double prime of 100. And so if I plug, this is a cube, so I'm just looking at the number itself. So -100 would make this positive over negative. So we know that's negative concave down, and that matches. And then this would be positive over positive, which is positive. So we know it's concave up, and that matches. So concave down, concave up, everything is good. So do we have any inflection points? And you may say, oh, -1. -1 is not a point. So no, there are no inflection points. Our numerator did not give us anything. Our denominator had a domain no. So no inflection points. So it is concave up from -1 to infinity, and it is concave down from -infinity to -1. And so now we just need to trace that onto our graphs. So over here, we know it's concave down, like that. And remember, always approach the asymptote. So when you're drawing your concave up, it's just going off to infinity and off to infinity, approaching the asymptotes. And there we go. There is our rational function. Thank you.